we've been looking at the graphs of rational functions, you may have noticed some other types of asymptotes. For instance, the graph of 1 over x also has a horizontal asymptote right at the x-axis. The graph of 1 over x squared also has a horizontal asymptote at y equals 0, or the x-axis. X plus 1 over x minus 1 has a horizontal asymptote at the line y equals 1. And some rational functions don't even have a horizontal asymptote. Here's the graph of x squared minus 4 over x minus 2. And notice that it doesn't have a vertical asymptote or a horizontal asymptote. This is probably not what you expected the graph to look like. There's no horizontal asymptote, vertical asymptote. There doesn't even seem to be any curvature to this thing. So how do we tell if a graph is going to have a horizontal asymptote and where that horizontal asymptote will be? Well, here's a quick summary. What we need to compare is the degree of the numerator and the degree of the denominator. That is highest power of x in the numerator and highest power of x in the denominator. If the degree of the numerator is less than the degree of the denominator, then our horizontal asymptote will happen at y equals 0. If numerator and denominator have the same degree, then we're going to reduce the leading terms, and whatever fraction is left over, that is where our horizontal asymptote will be. If the degree of the numerator is bigger than the degree of the denominator, then we simply have no horizontal asymptote at all. Let's try a few examples. If we look at little g of x, the degree of the numerator equals 1. That's the highest power of x that we see. If we look at the degree of the denominator, the degree is 2. That's the highest power of x that we see. Since the degree of the numerator is less than the degree of the denominator, we will have a horizontal asymptote, and the horizontal asymptote is the line y equals 0, the x-axis. As we look at h of x, the degree of the numerator is 3. The degree of the denominator is 2. Since the degree of the numerator is bigger than the degree of the denominator, we do not have a horizontal asymptote. There is no horizontal asymptote. And looking at k of x, the degree of the numerator is 4. The degree of the denominator is also 4. Since the degree of the numerator is equal to the degree of the denominator, we will have a horizontal asymptote. But where is it? Well, what we need to do is focus on these leading terms. 6x to the fourth over 3x to the fourth reduces to 6 over 3, which also reduces to 2. So our horizontal asymptote is the line y equals 2. There is one more type of asymptote that we should talk about. That's called an oblique asymptote. And it's not vertical, it's not horizontal. Some books will call this a slant asymptote because it's really more like a slanted line that the graph will follow. If the degree of the numerator is exactly 1 more than the degree of the denominator, then long division or synthetic division will give you the oblique asymptote. So these asymptotes only happen when the difference in degree is 1, and we'll find the asymptote by doing division. Here's an example. A of x equals x squared plus 3 over x plus 1. Notice that the degree of the numerator is 2, and the degree of the denominator is 1. This is the specific circumstances where we get an oblique asymptote. Degree of the numerator is 1 more than degree of the denominator. So let's do division with x squared plus 3 divided by x plus 1. So I'll set this up as synthetic division. Since we're dividing by x plus 1, we put a -1 outside this little framework, and then the coefficients of x squared plus 3 is 1 for the x squared, a 0 placeholder for the x, and a 3 for the constant. So when we do our process of synthetic division, we add 1 plus nothing is 1, -1 times 1 is -1. 0 minus 1 is -1. -1 times -1 is +1. And our remainder turns out to be 4. However, the remainder is not really important here. What we have to focus on is the 1 and the -1. This represents the expression x minus 1. And so x minus 1 will be the slanted line that will act as an asymptote.
So here's the graph of x squared plus 3 over x plus 1, along with the graph of y equals x minus 1. And you can see that as you go off to the right and to the left, the graph does follow that straight line.
And don't forget this vertical asymptote at x equals -1.
Next, we'll look at b of x, and notice that the degree of the numerator is 3 and the degree of the denominator is 2. So the degree of the numerator is exactly 1 more than the degree of the denominator. That's when we have an oblique asymptote. Now, to find the oblique asymptote, we're going to need to do division. But synthetic division is not an option here. We're going to instead have to do long division. So we need to ask ourselves what we need to multiply x squared by to get x cubed. And the answer is x. When we actually do that multiplication, distribute the x, we get x cubed minus 36x. Now we're going to draw the line, change the signs. X cubed minus x cubed is 0. Drop down that negative 2x squared. Negative x plus 36x is plus 35x. And we're also going to drop down that -1. Next we ask, what do I need to multiply x squared by to get negative 2x squared? The answer is -2. When I distribute that, I'll get negative 2x squared plus 72. Now again, we'll draw the line and change the signs. Negative 2x squared plus 2x squared cancels out. We bring down the plus 35x and a minus 73. So that's our remainder. But the important part of this is the quotient, the x minus 2. That part is going to be our oblique asymptote. So here's the graph of x cubed minus 2x squared minus x minus 1 over x squared minus 36, along with the oblique asymptote y equals x minus 2. And you might think to yourself, well, it doesn't look like that graph is following along that straight line at all. But notice what happens as we start to zoom out and reveal the other parts of the graph. So notice that those two branches do follow the oblique asymptote really well as we move off to positive and negative infinity.
Finally, I want to clear up one common misconception that people have about asymptotes. Some people think that a graph of a function can never touch an asymptote, and while that is true of a vertical asymptote, it is not true of horizontal asymptotes. It is okay for a graph to touch the horizontal asymptote, as we'll see in a couple of examples here. Let's take a look at r of x, which is negative x squared over x squared plus x minus 6. So since the numerator and denominator have the same degree, we should be able to find the horizontal asymptote by reducing negative x squared over positive x squared. Well, negative x squared over x squared reduces down to -1. Well, here's a graph of r of x along with the line y equals -1. And you can see that as we move off to the left and to the right, our graph seems to be following that horizontal line. But let's zoom in a little bit more closely and notice that the graph of r of x actually crosses that horizontal line, so that as we move off to the right, the graph gets closer and closer to the horizontal line from above, not from below. As another example, we can look at this function t of x, which is 3x over x squared plus 1. This time, since the degree of the numerator is smaller than the degree of the denominator, we should have a horizontal asymptote at y equals 0. And here's the graph of t of x along with the line y equals 0, also known as the x-axis. And we can see as we zoom out that the graph definitely approaches the x-axis as we head off both to positive infinity and to negative infinity. But right here in the middle, right at the origin, the graph crosses that horizontal asymptote. So hopefully I've cleared up that misconception that a graph can never touch an asymptote. That myth should be busted now. In some cases, there are values of x where the function can touch or cross the horizontal asymptote. Thanks for watching this video, and now go out and try some of these problems yourself. We'll see you next time.